Hello?
Everything is the mic's on. It's great. Can you speak?
Hello, everyone.
Is it just too far away? Oh, it's on.
Okay.
Maybe a little higher.
Is it better now?
I can hear you. Okay.
Hello, everyone. Can you hear me?
Okay. Yeah.
All right.
Okay.
All right, so hello, everyone. My name is Akash Pardeshi, and I'm here with Mendis, and today we'll be presenting our work, CERES. So over the past years, there have been many popular works using equality saturation in various domains. One of the early applications was Herbie. Herbie is a tool that improves the accuracy of floating point expressions. And more recently, there have been several works like Diospyros, Isaria, and Misal that use equality saturation for compilers. So I'm assuming here that everyone is familiar with equality saturation. I just want to introduce some terms I'll be using. Equality saturation has two phases. There is first the exploration phase where the rewrites are applied. And this exploration phase continues until either saturation is reached or more commonly a resource limit, which typically a node limit is reached. Once the exploration phase is done, that EGRAPH is called the explored EGRAPH, and that's what's passed into the extraction phase. All right. So recent research on equality saturation has greatly improved many aspects. For example, there is egg and egglog, which have made equality saturation fast and extensible. There is ruler and enumo, which can synthesize rewrite rules so that domain experts don't have to manually develop them. And there is smoothie, which makes ILP-based extraction much faster and can handle nonlinear cost functions. So despite all these advances, equality saturation still has some limitations, such as its unfavorable memory scalability. To see what I mean, let's go through some of the drawbacks of using a large node limit. The first drawback is increased memory consumption. So we observed that in real equality saturation applications, the exploration phase usually stops due to reaching the node limit and not reaching saturation. And so with a very high node limit, we're basically letting the EGRAPH grow very large, which takes more memory. So as a concrete example, consider Herbie. Internally, Herbie uses equality saturation to generate candidate expressions and then simplify them. So in this plot, the x-axis shows the node limit that we set for the calls to equality saturation inside Herbie. And we go from 8,000 nodes, which is the default that Herbie uses, all the way up to 128,000 nodes. And on the y-axis, we show the bit error of the floating point expression for all the expressions in the Hemming benchmark. So we see that for the default node limit of 8,000, the error is 21 bits, and if you go all the way on the high end to 128,000, the error drops down to 10 bits. And so this is a very significant reduction. And if we take a look at one specific input expression, so here's the input expression. It has 29.9 bits of error. And if we run Herbie with its default 8K node limit, it produces this expression, which basically does nothing and doesn't reduce the error at all. But if we run Herbie with 128,000 node limit, it produces this expression, which actually has almost zero error. So this shows that by using high node limits, Herbie can achieve significantly better application results. But these better application results come at the cost of more memory consumption. So this plot shows that as the node limit increases, the memory consumption grows linearly. And at the highest node limit of 128,000, Herbie is taking more than a gigabyte of memory. And so this high memory consumption is one reason why the Herbie designers decided on such a low node limit of only 8,000. So the high memory consumption we see isn't specific to just Herbie. We see that Misal also regularly takes 1 to 2 gigabytes of memory per benchmark. And Diospiros uses even more memory, up to 35 gigabytes in the worst case. So many applications using equality saturation are facing high memory consumption. And given the tight linear relationship we saw between the node limit and memory consumption, for the rest of this talk, we'll be using the node limit as a proxy for the memory consumption. Okay, so the second drawback is increased rewrite search time. Even the fastest current E-matching algorithm takes time polynomial in the size of the E-graph. So with a larger E-graph, searching for rewrite matches will take longer. And the final drawback is with the extraction phase. As someone mentioned before, extraction is an NP-hard problem, so there are both exact and heuristic methods. And these exact algorithms are based on ILP, which do not scale well to large E-graphs. For example, even with Smoothie, extraction takes around 30 to 40 seconds on relatively moderate size E-graphs with only tens of thousands of nodes. So therefore, using a high node limit comes with several drawbacks affecting the practicality of equality saturation. But we've also seen that applications kind of need to use high node limits to get good results. And so thus, application designers have to make a choice between practicality and getting good results. The solutions to this memory scalability problem kind of center around rewrite scheduling. So a rewrite scheduler controls which rewrites are applied in each iteration of the exploration phase. For example here, a rewrite scheduler would control which rewrites are in the set R1, and then which rewrites are in the set R2, etc. And there are two types of schedulers. First is static scheduling, where the scheduler determines the schedule ahead of time without seeing any specific input expression. So once the scheduler decides on a schedule, it's fixed and will be used for whatever input expression is fed in. So this schedule would be decided ahead of time, and then for any E-graph that comes in, you then apply these rewrites to get the E-graphs. Examples of static schedulers include simple scheduler, which just applies all rewrites at every iteration, and also Isaria, which consists of 3 phases with different subset of rewrites in each phase. Clearly, static schedulers are limited in the amount of information they have with which to make their scheduling decisions. So the next type of scheduler is a dynamic scheduler. A dynamic scheduler decides its schedule at runtime based on dynamic information. So based on whatever initial E-graph it sees, the scheduler can then pick its rewrites R1 and get a new E-graph E1. Based on this set of information, the scheduler can then pick its rewrites for the next iteration, etc. So examples of dynamic schedulers include backoff scheduler, which is the default in egg. Backoff scheduler uses an exponential backoff heuristic to temporarily disable rewrites which are matching too often. And of course, this requires tracking how many times each rewrite is applied at runtime, so this is a dynamic property. Another example is MCTS GEB. It uses a Monte Carlo tree search algorithm to decide on what rewrites to apply. And this is also dynamic because to do the tree search, you need to know the E-graph, which is only known at runtime. So if you consider this example, this is a very big randomly generated math expression. And if we run equality saturation with simple scheduler, the explored E-graph has 6,000 nodes and gets a cost of 3,300. And if we run backoff scheduler on the same expression, for the same number of iterations, it produces a smaller E-graph with 5,000 nodes and achieves a lower cost of 3,200. So this shows that backoff scheduler is able to use its dynamic information to make better scheduling decisions and get both a lower cost, which is better quality, and a smaller final E-graph, which is less memory consumption. However, current schedulers have a limitation. They focus on controlling the size of the E-graph without considering the quality of expressions contained within it. For example, backoff scheduler is explicitly designed to control the size of the E-graph by disabling those rewrites which match too often. However, some of those rewrites might be important towards getting high-quality, low-cost expressions, but backoff would just disable them. So as we've seen with Herbie, which actually uses backoff scheduler, you still need to use high node limits to get good quality. and this affects practicality. So to address this limitation of existing rewrite schedulers, we introduce CERES. CERES is a dynamic rewrite scheduler that biases the exploration phase towards high-quality expressions. It does this by identifying what we call important rewrites. Important rewrites are those rewrites which contribute towards the search for high-quality expressions. And redundant rewrites are the rewrites that do not contribute towards this search. So CERES enables memory-scalable equality saturation. It ensures that the eGraph never exceeds a specified size and a specified node limit. And under this node limit, CERES can find equal or better quality expressions than is possible with current rewrite schedulers. And so this allows CERES to go with a much smaller node limit, which is in the region of practical memory consumption, while still getting equal or better results. And second, CERES is portable to many diverse equality saturation applications. Later in this talk, we'll show our evaluation results on 3 different applications. So first, I want to give some intuition behind what important rewrites are. So consider this eGraph and these 2 rewrites. If we apply the rewrites, we get this eGraph, and the root E class represents these 2 expressions. So the first expression has cost 5, and the second one has cost 6. So we might be tempted to say that the first rewrite was more important since it brought down the cost. But if we keep rewriting, we would find that the first expression's cost doesn't go down, but the second one goes all the way down to 4, which is that optimal expression from earlier. And so therefore, we say that the first rewrite is redundant, and the second one is important for this specific eGraph. Okay. So there are challenges to this approach of deciding on important rewrites. So I said earlier that an important rewrite is one that contributes towards the search for high-quality expressions. The problem is, we don't know beforehand whether an expression is high quality or not. And furthermore, with current rewrite schedulers, that most optimal low-cost expression might be out of reach within the node limit. Second, we cannot test rewrites for importance independently. It's very common that multiple rewrites might need to be applied in a single iteration for subsequent rewrites to be applied in later iterations to get towards that best expression. And so this means that if we can't test rewrites independently, we have to test subsets of rewrites together. But that means if there are n rewrites, then there are 2 to the n subsets. And given that real eGraph applications have hundreds or thousands of rewrites, you can't. That's just intractable to search overall combinations. And finally, the set of important rewrites is a dynamic property of an eGraph, which means that if we can somehow find what this set of important rewrites is for one eGraph, then later on when we have another eGraph, we're going to have to do this search again to find the set of important rewrites for that eGraph. All right. So now let's talk about how we formally define what the set of important eGraphs is for a given the set of important rewrites is for a given eGraph. So I said that we need to test subsets of rewrites. So we want to find some subset Ri that minimizes some objective function. So what should this objective function be? Well, one natural thing we can do is for the subset Ri in question, we can take our initial eGraph, we can apply that subset for one iteration, and then apply all rewrites until reaching either saturation or the node limit. And that tells us 2 things. So first, from that final eGraph, we can get the cost of the extracted expression. And second, we can also check, we can get the size of the eGraph in which that expression first appeared. So now this is our final objective function, and it has 2 pieces. It says that we want to get low cost, and we also want the eGraph to not explode. So note that we can reduce the size of the search space by only considering rewrites which match in the eGraph. Any rewrite which doesn't match isn't going to affect this cost function. Here we have the distribution of how many rewrites match. This is for Herbie. So one thing to note is that out of the 200 rewrites for Herbie, there's never more than 100 matching rewrites, so that already cuts down the size. But obviously, 100 matching rewrites is still too big. The other important thing to notice is that 20% of the time, there are actually 5 or fewer matching rewrites, and 5 is small enough that you can just exhaustively try all 32 combinations. But for most of the time, the combinatorial optimization problem is too big for exhaustive search. So what can we do instead? We can use the cross-entropy method. So the cross-entropy method is an established technique for finding solutions to combinatorial optimization problems. And the algorithm goes like this. We start with all the rewrites which match, and we give each of them an initial probability of 0.5. We don't know if they're important or not important at the start. From this distribution, we then take n samples, where each sample is a subset of rewrites sampled according to that probability distribution. We then sort these samples based on how well they do according to the objective function. And we kind of take the best samples that we've seen. We look at which rewrites are in those best performing samples and use that to update the probabilities. So now we have new probability distribution, and we repeat the process. We take new samples, again sort them, take the best samples, update the probabilities again. And after some iterations, we'll end up with a kind of distribution that is clearly divided into some rewrites that have probabilities close to 1 and some probabilities close to 0. And so the important rewrites are those rewrites which end up with high probabilities. All right, so now I'll pass it to Devansh.
Hi. So now on to some concrete statistics on the statistics that we collected when we were evaluating CERES against existing schedulers. So since again, CERES is specifically designed to address memory scalability, we essentially had 2 hypotheses and we want to test them. The first one, that CERES can achieve better expression quality given a fixed memory budget, and as a corollary that it requires lower memory budget to reach similar expression quality. Our evaluation will go over 3 different applications. We will start with a test application of math, which with node limit as 5K. Then we'll move to a popular application of Herbie, with node limits going from 4K to 96K. And then eventually we will look at a compiler application of DSP vectorization called DSP-ROS, which has node limits as high as 20 million, which often requires a server machine to kind of meet its memory demands. So math is effectively a simple algebra language, and it has been used in prior works like MCTS as well for evaluations. So similar to MCTS, we kind of randomly generate 50 expressions and evaluate on that. We aim to analyze 2 key metrics, one being the expression cost, and the second relative to the baseline, which is the back of scheduler, and the second metric being the relative size of the final eGraph. A good scheduler should ideally lie in the bottom left quadrant, since that implies smaller final eGraphs and lower expression cost. So prior work, MCTS, the scatter plot of it does show that it does achieve lower cost at some points, but it also has cases where it does have worse cost. And consistently, it has larger eGraph sizes than backoff. CERES, on the other hand, is consistently in the bottom left quadrant, and we almost always achieve lower cost and smaller eGraphs compared to backoff. So that's the first positive result. Now let's consider Herbie, which is again has been commonly used in a lot of evaluations like egglog, ruler, and NEMO papers. So Herbie uses backoff scheduler under 8K node limit, and that's its default scheduler. And to the best of our knowledge, we couldn't find any prior works similar to MCTS which have been tuned for Herbie. So our evaluations kind of restrict to backoff and CERES. We select the Hamming problem set, which effectively has around 800 equality saturation calls, and these are eGraphs we evaluate on. Again, to show versatility, we consider 2 rule sets, one being the main Herbie rule set from the Herbie repository, which consists of 200 expert written RIA tools, and another around 300 RIA tools which were synthesized using NEMO. Right, so again, looking at the main rule set, over here we plot the relative expression cost, geomeaned over all the 800-ish eGraphs in the y-axis against the node limit that we set for the engine in the x-axis. As we increase the node limit, we see that the relative cost decrease for backoff. And again, lower is better since we want to have lower cost, which is better expression quality. When we look at CERES, for similar node limits, we kind of observed even lower costs. So at around 8K, CERES achieved around 20% lower cost than backoff, and the improvement got better, and around at 64K, it was 33%. And overall, it kind of takes around, so it takes 96K node limit for backoff to achieve similar expression quality as what CERES can do at just 8K. So overall, we achieve like close to, you require 12x lower memory budget to kind of reach similar expression quality. We repeated the same experiment for NUMO synthesized rule set, and similar to last time, backoff also was tapering out around 20% reduction at around 96K. And however, this time CERES had even lower costs, reaching up to 80% reduction. We believe this is primarily due to that the synthesized rule set includes several rewrite rules that often cause explosive eGraph growth. And since CERES is intelligently turning off redundant rewrites, it allows us to explore to larger depths and find even better expressions. And even at like 12 times lower memory budget, which is like CERES at 8K, it can achieve better expression quality than backoff at 96K. So, and also CERES essentially has more benefits, especially when you're using a synthesized rule sets, which are more prone to having such explosive eGraph growth. Finally, we have the evaluation on DSPROS, which is a compiler application for DSP vectorization. The developers for DSPROS prefer to use 10 million as the node limit, which when they were benchmarking the 21 DSP kernels. So we again do a similar experiment as Herbie, though this time the default is backoff 10 million. And we see that when we do pick smaller node limits like 10K or even 100K, it does lead to higher expression cost, which does justify developers' choice of using 10 million as the default node limit. On the other hand, CERES can match or even beat the baseline with just 20K node limit. So CERES at 20K is effectively 60% lower cost than backoff at 20K, and it has similar geomean statistics as 500K node limit for backoff. We did another analysis on, again, DSP kernels, but this time plotting them with the x-axis being the problem size or the eGraph size for individual DSP kernels, and the y-axis being the node limit needed to reach cost convergence. So we saw that we need 2 million node limit to achieve good quality expression for all DSP kernels when you are using backoff. For CERES, we were able to do the same and reach good quality expressions at just 20K for all DSP kernels. So around 100x lower memory budget is needed for the developers when they want to benchmark these DSP kernels. In summary, we kind of validate our two hypotheses that CERES achieves better expression quality given a fixed memory budget, and it can achieve similar expression quality at a much lower memory budget. Overall, we presented CERES, a new dynamic rewrite scheduler, which enables memory-scalable equality saturation by identifying the set of important rewrites to be applied per iteration. Thank you.
Thank you to you both. We have time for a couple questions before we head off to break.
Great talk. So I have a few questions. So first, it seems besides important rewrites, you can, like different e-nodes also have a different importance, right? Have you considered, say, important e-nodes or e-classes?
So typically in eGraphs, you don't delete e-nodes or e-classes once they are added, and typically the way to control whether they should be added or not is by enabling or disabling rewrites. So that's what we effectively, so we control not adding those, maybe say redundant e-nodes by not allowing those rewrites to run for that particular
I'm thinking of the scenario where, for example, some e-classes are like deep in the past. So even if you over-optimize these, they are not likely to produce a better overall optimal program.
So usually, usually those e-nodes or e-classes will typically either not be generated when we are in the prior iterations, because currently when we are running equality saturation, it will just apply all rewrites, so those e-graphs and e-nodes may be generated. But because CERES is being applied from iteration 0, those e-nodes and e-classes, if they are not making the overall cost better, they will not be generated in the process.
Okay. Sorry, just another quick question. So could you talk a little bit about the runtime overhead of the cross entropy method?
Right. So looking at the same node limit, certainly CERES is slower than backoff because backoff doesn't have to make any decision. But when we do compare at similar expression quality, so when we look at backoff for 10 million in Days bureaus, that's actually 3 times slower than CERES at 20K. Because again, smaller node limit, the search time, the extraction time, all of those times are much slower because it's like almost 100, 200x memory reduction.
Just to riff on Yihong's question a little bit, I think one thing that we might be seeing here is a deficiency in the egg API or the egg way of doing things. I think maybe Yihong was suggesting or pointing at a rewrite scheduler that not only turns rewrites off and on, but localizes them in some way, saying like, okay, let's apply this rewrite to this part of the eGraph, but not this other part.
Yeah, so that's also one thing we were considering before. Instead of doing things at the granularity of individual rewrites, potentially you could do things on specific rewrite matches. Like that's still something that's under the control of the scheduler. The scheduler doesn't have to apply all the matches for a rewrite. Yeah, so that's something we will look into in the future.
Yeah. So I just pulled like the latest master, the main branch of Herbie, and it does actually find the log1p 1/n rewrite. So I'm not sure. This might the rewrite set has changed a lot in Herbie. So we might have just added this rewrite recently that causes it to find the rewrite. No. So has Herbie become better? Is that the reason? Yeah. Just pointing it out.
Yeah, so I think the rewrite set that we were using might be a bit old. It's kind of at the same timeline as NUMO, which is a couple of years ago. So the main rewrite set we are using is not. And also, the same issue was also coming with the NUMO synthesized rewrite, where some expressions were, again, log1p is one example, but there was the kind of trend was still visible in like different rewrites as well.
Yeah, I also want to point out for the log-p example, so yeah, it is true that we were using the rule sets that NUMO used in their evaluation, so we could have fair comparison. For the specific log example that I pointed out where it goes from 29 to 0, that was using the NUMO synthesized rule set, so not the Herbie developer one. I would expect that the Herbie developers take this into account and have rewrites for it.
Okay, let's thank our speakers one more time.